Hey guys, so in this video I'm going to be going over the Kronig Penney model, which is the simplest toy model that I know for describing electrons in periodic potentials. And this is going to be particularly useful for the remainder of the video series on semiconductor physics, because I'm going to derive a dispersion relation in this video. It's going to be quite a long one. And then in another video, I'm going to discuss how that dispersion relation can show us the existence of band gaps. And then after that, we're just going to talk about semiconductors, right? And then we can be at peace. This is the only hard physics I'm going to do for this sort of video series. Now, the Kronig Penney model starts off by talking about a 1D crystal lattice. Wherein we're gonna have atoms, right, in a straight line, right? If here I'm just gonna have another atom, and then if I go here, I'm gonna have another atom, and they're all gonna be equidistant with distance a. This is gonna be called the lattice constant for this lattice, right? Now, when you're talking about 1D lattices like this, what you can do is you can notice that right there, a periodic structure. If I split this distance in half between consecutive atoms, then I just take a look at this thing in the middle. If I were to then grab this and copy it many, many times over, I would actually get the entire lattice back, right? If I then did that, right, then these distances are getting a bit off, but you get the point. If I do that over and over again, these unit cells are exactly the same thing. That's what a unit cell is. And I'm going to be focusing on one unit cell. So I'm going to erase this. I'll probably end up drawing continued atoms again a few times, just to make sure. So I'm going to have my one unit cell. So I have my one atom. And then the barrier to the end of the unit cell is going to be, have the axis under. It's going to be minus a over 2 and a over 2 this way. And the atom is going to be centered at x equals 0. So what I'm now going to say is that, hey, we're going to be discussing electrons, right? We want to know the behavior of electrons in this lattice. And electrons are going to behave differently when they're closer to atoms than when they're further away. That makes sense, right? So what I'm going to say is that I'm going to have a energy barrier. So I'm going to have the case that the potential of the unit cell will range from V is equal to 0 to V is equal to some V naught when we move through the unit cell. And I'm going to define it that in a region around the atom, where these points are also equidistant, we have this big potential barrier, right? So here the potential, and within this region, the potential is going to be equal to V naught. Meanwhile, outside, it's just going to be equal to 0. And this isn't exactly the true picture because realistically atoms act as potential wells, not barriers. But sign choice, especially when you're talking about energies, is kind of arbitrary. And this gives out the expected behavior, and it's slightly simpler mathematically, so we're going to keep it at that for now. Now, with that, we can start talking about wave functions. So, we have the case that in this region, our potential energy is 0. In this region, the same is true, and then in this region, between these two equidistant points, which I'm going to now call b over 2 and minus b over 2. And these are also periodically going to be the same. So what that means is if I move over to the next atom, from that next atom, if you go b over 2 either side, our potential is also going to be equal to b naught, some positive number. With all of that, we can start solving our Schrodinger equation. Right, our time-independent Schrodinger equation. So we write minus h bar squared over 2m. And we're in the one-dimensional case, so we don't have to worry about the Laplacian. We can just write this as the differential operator in x, right? And this is going to be added to the potential, and then this whole shebang gets multiplied by our wave function, and then that is going to be equal to the energy multiplied by the wave function. So we have two cases here, right? We have the case where the potential is just equal to v naught, and the case where the potential is equal to 0. But it's not a function of x. Well, it is in a way, but not exactly right. In both of these cases, these are just numbers. So we don't have to worry about this x dependency, and it makes solving the equation quite easy. I'm gonna call this region to the far left the free electron region, right? And then I'm gonna call this the right free electron region. Because in these parts of the lattice, the electron acts as a free particle completely. It has no potential. Well, it won't act exactly as a free particle, but for the sake of argument, it has the Schrodinger equation of a free particle. And then in the point where we're at V0, we're just going to say that this is our barrier. And it's going to be around the atom. So we have three cases to solve for. So for the free electron cases, what we can write is that this potential is just gone, right? Potential is equal to 0. And we have this thing, the free electron Schrodinger equation. And this is just a linear second order differential equation. We move the constants out to this side, and E is also a constant, so we just have that the second derivative of the wave function with respect to x is equal to 2me over h bar squared multiplied by the wave function. And you're just going to have to either trust me on this or know it, but the solution to this kind of equation looks like this. Oh, also, the negative sign is actually very important. So the equation looks like so. We have that psi of, let's first write L3, is equal to A e to the ikx plus b e to the minus ikx, where k is just the square root of this factor. So this thing is equal to k squared without the negative sign. So that's the wave function here. Now, for the right, we actually have exactly the same equation. The only nuance is that we are solving these separately. So all I'm going to say is that these normalization constants are just like different letters. But these parts, the exponentials, are going to be exactly the same. So psi of r3 is going to be equal to c e to the ikx plus b plus d e to the minus ikx. Right? And the last thing we have to solve for is for the barrier. And at the barrier, we do have a potential, but it is some constant number, right? Instead, the Schrodinger equation becomes this. Becomes V naught psi is equal to E psi. And this is solved in exactly the same way, but we just have to rearrange a bit more. We have the second derivative of the wave function with respect to x is going to be equal to minus 2m over h bar squared multiplied by e minus b naught. And obviously this whole thing is multiplied by psi. Now, for the sake of simplicity, we're going to say that v naught is larger than e, and so this expression is negative, and so actually the whole thing is positive. So we can write this instead as so. V naught minus e, where this expression is positive. And this has almost exactly the same solution form, except that now we don't have any negative square roots anywhere, so we get rid of i's. So the psi at the barrier is going to be equal to f e to the kappa x plus g e to the minus kappa x. Yeah. Now we have all of these, and we just now have to relate them somehow. And we can do this using the boundary condition, right? What we know is that the wave function and its derivative in space must be continuous. So here we see that there's some breaking points, right? Where we have minus b over 2 and b over 2, this right free wave function, and this barrier wave function must be equal at that point. And so must their derivatives. And the same case is true for the left free wave function and the barrier wave function minus b over 2. So we can write that as so. We write that psi barrier at minus b over 2 is equal to psi L free at minus b over 2 and psi barrier at minus b over 2, its derivative is equal to here. Exactly the same expression. And the reverse is true for the other side, so psi barrier of b over 2 is equal to psi r free b over 2 and psi barrier prime its derivative b over 2 must be equal to the derivative of psi r free at b over 2. So these four equations are quite important. I'm gonna get rid of this diagram now. We don't really need it anymore. So we have these four equations and these three definitions as well. Now, to put this all together, we also need to consider one other thing, which is Bloch's theorem, which tells you how wave functions act due to periodicity in a periodic lattice. Now, what I mean by that is, or what Bloch's theorem states, I might as well just write it, is it tells us that, hey, if we're in a case where the potential is periodic, which is true, we've shown it here that, like, if you move by A, you're in exactly the same point in a different unit cell, but physically that unit cell is identical to the previous one. So the potential at that point is going to be the same. And as a result, the wave function follows this theorem. So A, as we remember, is the distance between different atoms on our lattice. And therefore also the distance over to the next unit, to the exact same point in the next unit cell. So psi of x plus A is going to be equal to some phase factor with another k, kb, which is the crystal wave vector. And for this purpose, its definition is not that important. You just kind of have to accept this theorem as is. Proving it is possible, but it will take time that I don't want to use. And that is going to just be equal to, and multiplied by this lattice vector. So this is just a phase factor as well. Physically, this does nothing to the wave function. So what we see here is that in a periodic potential, if we move over by a lattice vector, then really we just change the wave function by a phase factor. Physically, it's almost identical. So where do we use that? Well, we use that to relate the left and the right wave functions. So the left free and the right free. Because, right, those are separated by A, right? They're separated by this factor. If you remember the diagram, they're at opposite ends of the unit cell. So that means that they must follow Bloch's theorem as well. So to this series of 4 equations, we now add 2 more. And we say that this psi r free is x plus A. So psi r free is going to be equal to e to the ikBA, our phase factor, where kb and a are both constants and I is, as of course we know, Euler's imaginary number. And this, the psi L free, conversely, also, their derivatives match in exactly the same manner. So, psi r free prime, or dash, whatever, is going to be equal to still this constant offset factor, and the derivative of psi L free. And now we have all of the equations that have to be satisfied simultaneously for our toy model to be physical. Right? We're saying that all of these things have to be true from the quantum mechanics we've used in this lattice potential. So our last step is simply to solve, which is the hardest step. Now, the way you do this, and I'm not going to do it in its entirety, but I'm going to show how you set up this matrix multiplication. So I'm back, and I've written all of these equations out. This was literally just plugging in the wave functions that we found by solving the Schrodinger equation into all of these boundary conditions that we defined. And the process is pretty much done here. Now, what we're trying to solve for are the unknowns, and this is where beautiful linear algebra comes in. And all we have to do is say, well, hey, we can rearrange all of these equations, set them to equal to 0. And in that case, we have 6 simultaneous equations, I guess, 6 linear equations in 6 different factors, right? In A, B, C, D, E, F, G, right? These are all of the unknown factors that we can see throughout. So we can write this as some matrix of all of these equations multiplied by our column vector A, B, C, D, E, F. Did I skip F? I skipped E. Okay. A, B, C, D, F, G. And we know that this will give us out these. Right? If we have all of these equations and then we just move every factor in every equation to only one side, then we can consider each equation as being an equation in 6 variables. It's just that the coefficient for some of them is 0, right? We can write this matrix M as therefore then every time that in each equation a factor is multiplied by an exponential. I'm not going to do all of that because it will take forever. But trust me and trust you, the math has been done for us. All we have to do is physically say, and mathematically, that if we want to show that all of these equations have solutions that follow this form, where we have that whole matrix in terms of all of those equations, multiplied by the 6 column vector, equaling the trivial solution, then we know that we have to have the case that the determinant of M of that matrix has to be equal to 0. Right? And if you do all of that, if you actually do the linear algebra, and I know this might sound a bit anticlimactic since I'm not actually doing the linear algebra, but trust me, no one does the linear algebra. It's way too hard. You get out the following dispersion relation. Now, if we then solve for our beautiful matrix and find the determinant when it's 0, we end up with this final relation. Now, this is one hell of an expression, and I'm going to use the following video to explain how you can get from this that bands exist and that there are band gaps in certain situations. But yeah, throughout all of this, I would definitely say don't try that matrix multiplication. It's not worth it. You can do it. You can do it by hand, but it's very, very time consuming. But what we have done successfully is, well, we quantum mechanically defined our wave functions in a unit cell of a periodic lattice. We then used our boundary conditions we use boundary conditions and Bloch states to get out a dispersion relation, right? And that is what we were looking for. So success.